So let's take a look at what is energy. Now, if we try to define or understand what energy means, it's kind of difficult to define it. Um, but we have already heard this word before in biology and chemistry classes in the form of sunlight, glucose, ATP, chemical bonds, or in hot gases. So we've already familiar with this word, but it's hard to define what it actually means. So if we have to define what it is, we can define it as the ability of an object to make a change. Now, the ability of an object to make a change is also not so clear how we can understand this term. So we have another definition where it says the ability of an object to do work. Now, it's easy to see what it means, but we are not clear about the definition of what is work then. So we'll leave with those two definitions and go back to the history of where energy word came from. Energy word came from a Greek word, which is energia, and it's written in this form that you can see on the screen. Now, this term or the energia was developed by Aristotle and to define what energy is. Energia has no direct translation to English. So it's frequently described as being at work, but it doesn't have a very clear definition of or translation from this word. Now, energy is a useful word, which helps us to note the patterns and the natural laws. Now, the patterns in nature can be explained easily with the concept of energy, and natural laws is where we will talk about the conservation of energy. We'll see this term later, but you will see that how it explains how the energy is conserved or remains constant. Now, energy is not an intuitive idea like we've already seen speed and force, push or pull. So those terms were kind of, you could understand what it means, but energy is not an intuitive idea. Now, energy comes in different forms. We'll talk about these forms in this class and we'll categorize these under the terms kinetic energy, which means that it's associated with an object in motion or any moving object will have energy, which is called kinetic energy. The other category we're going to term as potential energy. Now, this type of energy is associated with location or how the objects are arranged. So we'll use these two terms of types of energies. Now, again, we also have another type of energy, which is thermal energy. It's associated with the motion of the individual molecules, or if you want to look at a molecular level, then it's basically the kinetic energy in the tiny kinetic energy of the molecules. And we'll usually see this in the form of heat in our problems. Now, the two types of energies that we'll go in, energy is represented with the symbol capital E for energy, and the unit we use for energy is joule or capital J. Now, it's a scalar quantity that you need to remember. It does not have any direction, so you only need to give or describe the energy with the magnitude. So you do not require to give the direction for the scalar quantity. Now let's talk about kinetic energy in detail. So kinetic energy is the energy associated with motion of an object, or any object that is moving is going to have some kinetic energy. And the symbol that we'll be using is the capital E with the subscript K, or sometimes it can be written as KE. The equation for kinetic energy is half mv squared, where m is the mass of the object and v is the speed of the object. Also, keep in mind the speed will be squared. Now, if an object has a speed of 0, it means that it has no kinetic energy, because as you can see in the equation, if you plug in v as 0, it solves to be the kinetic energy equal to. Now, if V is large, or we have a larger object moving with a larger speed, it means that it's going to have a larger kinetic energy. Now, if we try to understand the relationship between V and the kinetic energy, if V is changing or increasing, the kinetic energy is also going to be increasing. We're going to take a look at some scenarios where we can compare the mass and the speed of the object. Let's say we have same mass, different speeds, and I'm going to show it with the bigger vector. As you can see, the bigger speed is going to have more kinetic energy. Now, if we have two objects with same speed but different masses, again, when we plug in the numbers in the equation, you can easily see that the bigger mass is going to have more kinetic energy. You also need to remember that kinetic energy is not going to be a negative number, and it cannot never be a negative number because mass cannot be a negative number. It's always positive. And the v or the speed, even if it's negative, notice that it's going to be squared in the equation, which means that a negative number will be squared to become positive again. So keep in mind kinetic energy can never be a negative number. Equation that the V is the quantity that will be. So let's take a look at units of kinetic energy. Let's write down the equation. EK is half mv squared. Now, if you want to write down the units, we know half does not have it in units, it's just a fraction. Energy is measured in joules, mass is measured in kilograms, and velocity is measured in meters per second, but it has to be squared. So joules will be equal to kilograms meters squared per second squared in SI units. Now we're going to take a look at the second type of energy that we're going to consider in this class, gravitational potential energy. It's the energy stored when an object is at a certain height in a gravitational field. That's how we will define gravitational potential energy. Now, we haven't talked a lot about gravitational fields, so we will see the energy of an object at a certain height in a certain gravitational field. We'll talk about this later. Now, more easier definition to understand that we'll be using in this class is energy stored in a system when an object is at a certain height. Now, it's very clear, but what we need to understand is how to measure the height, or how are we going to clearly define how the height is measured. So the symbol for gravitational potential energy is capital E with GP, or sometimes we will write it as GPE. And the equation that will help us calculate the gravitational potential energy is mgh, where m is the mass of the object, g is the acceleration due to gravity, which we already know is 9.81 meters per second squared on the Earth. And also keep in mind we're only going to use the magnitude. We're not going to use the direction or the negative number. H is the height of the object, and how we're going to measure it is going to matter. So So now we're going to take a look at the units for gravitational potential energy. But also keep in mind that this equation, mgh, only works when the object is placed near the surface of the Earth. As you move far from the surface of the Earth, it is going to make a difference that it's not going to be accurately measured. So let's talk about the units. Energy is measured in joules, mass in kilograms, acceleration in meters per second squared, and the height is measured in meters. So we come across the same. It's the same equation or same units we got for the kinetic energy. So joules is always going to be equal to the SI units, kilograms, meters squares per second square. Now, as I said before, how we measure the height matters, how we measure or calculate the potential energy or gravitational potential energy. So let's say we have an example of an object which is at a certain height or a cliff, And let's say the object is raised at a height of 2 meters, and the cliff also has some height of, let's say, 10 meters. So what can the height be in this case? Or what is the height? If we have to, the possible answers can be 2 meters, 12 meters, or maybe the distance to the center of the earth. They're all correct, but it depends on what is your reference point. So it all comes down to how you consider your reference point, or what is the point that you're going to consider to measure the height. So if we have to talk about reference point, it's going to be sometimes obvious in the problem, or you will be told how you are supposed to measure the height in a certain problem. So just keep in mind to read the problem carefully in order to understand how to measure the height. How you're deciding to measure the height is going to be um, either mentioned in the problem, or you have to be very consistent on what reference point you're using. So just a reminder that when solving a problem, you will be able to decide where to measure the height from, and if you're consistent or you use some reference point, everything is going to work out and you're going to get the right answer. So just keep in mind how you're measuring the heights, and that shall help you solve for the gravitational potential energy.